Perfect. Thank you. So, hi everybody. So, my name is Baran, and I'm a postdoc at Origin's Data Science Lab at Technical University of Munich. And this collaboration between me, Roderick Corominas, and Alessandro Giacchetto started like almost 4 years ago when I was doing my an internship at Humboldt University of Berlin with Gaetan Bro on representation learning and numeric geometry. And this idea came up, and since then we were working on this, and hopefully we'll continue work on this across different collaborators. So let's begin. So imagine that you have a problem in enumerative geometry. For example, you want to count curves over, let's say, smooth projective variety, and you want to basically compute intersections of this curve with a sub-variety, or like if there is a condition like it satisfies. So to make this basically space of solutions finite. And normally this like in the contemporary side of these computations are interactable. Even if you find basically a generating function, normally the computation follows a certain basically recursive procedure, which has a basically from computational perspective, it has an exponential or factorial blow up. For example, a simple classical example, like started from string theory. If you want to find the number of rational curves of genus 0 and degree d that lies on a quantic hypersurface P4, it grows with such basically such blow up. So then the question that we were asking was that, is it possible to actually surrogate this computation through an idea of neural enumerative reasoning model, which we want to satisfy certain conditions, to be able to extrapolate, to be able to provide certain type of reasoning over the data set. And if it is a big if this is a possibility, then we want to know if we can what we can learn from this neural enumerative reasoning model. Is it possible to extract knowledge from this mathematical world model of such neural networks? These type of questions are being asked even before this whole emergence of neural networks through basically what is called classically as experimental mathematics. So let's begin the mathematical picture, the mathematical background. Let n, g, and n be non-negative integers satisfying certain stability condition that's negative Euler characteristic to be non-zero. Then we can define the Line-Montfort compactified moduli space of algebraic curves if we introduce basically algebraic structure over the surface with genus G and n number of mark points. Then the dimension of this compact smooth orbifold would be 3G minus 3 plus n. And then one can associate a holomorphic line bundle over each mark point over the surface, and whose basically fibers are cotangent spaces defined on this curve. And then one can basically define the first one can compute the first Chern class of these line bundles, and one can basically, and then they are being denoted as the psi classes. Then if one computes the intersection of these psi classes, the first string class of these line bundles over the moduli space, then we know that in certain cases they belong, they are rational numbers, and they are non-zero, in a condition that the sum of exponents of these psi classes satisfy certain conditions like 3G minus 3 plus n as the dimension of the moduli space. Written in written in 90s found actually a very beautiful correlation between these intersection numbers and the correlators of the two-dimensional TQFT, topological quantum gravity. And then he conjectured that actually they are the coefficients of an exponential generating function, which satisfies an infinite tower of quadratic partial differential equations called KdV hierarchy. And then in the year after, with an even more beautiful manner, Kontsevich actually provided a proof to Witten's conjecture through the methods of combinatorics over and matrix models. And this was basically created a huge field of basically this modern. I mean, it started before, but afterwards, basically the whole modern enumerative geometry actually got a huge boost. And then 25 after, I mean, a lot happened within this time, but 25 years after, following the storyline of what we want to do, 25 years after, Kontsevich and Söbelmann provided basically an algebraic version of looking at these problems. So before we were looking at the problem from a geometric perspective, and now they provided another window through an algebraic perspective, which actually gives us a very interesting perspective, given that one can define this from a linear algebra perspective. This is actually, this gives us a free path towards basically the modern ML applications as we basically use the linear algebra in machine learning. I'll explain how. So they defined in 2017 what is called quantum area structure over a complex vector space. And they basically call these family of differential operators that satisfies certain algebra, Weil algebra. And they are being parameterized by this A, B, C, D tensors, which satisfies also certain symmetric conditions, certain certain isomorphisms and so on. But then they showed that actually there exists a unique formal partition function with coefficients fg(d1) to dn that is being annihilated by these differential operators. And they call this fg(d1) to dn. This d1 to dn are actually I'll tell you shortly what they are, but they are symmetric, meaning that they are permutation invariant. They call them quantum area structure amplitudes that are being defined, determined basically recursively merely based on the initial data A, B, C. And this the recursive computation that being defined for them actually are topological recursion. So being the topological recursion creates a geometric perspective towards computing certain intersection numbers. In our case, psi-class intersection numbers. They provided an algebraic perspective to the whole picture. And then if you fix ABCD to be like in such forms, this basically depending on the problem that you want to do. So they provided basically a machine that you provide ABCD, and then you get out of it you get basically certain coefficients. So you could get basically homological field theory intersection numbers. You could get topological field theory, topological quantum field theory amplitudes, and so on, given that you change this ABCD and the basically formal monomials that you define over your vector space. And then if you choose ABCD to be such, then one can show that the psi-class intersections are being coincide with exactly these FG(d1) to dn. And d1 to dn are actually those basically exponents of the psi-classes or the partitions that basically satisfy this condition and to be like non-zero, that they are equal to 3g minus 3 plus n. So we saw that basically one can compute these coefficients through basically the methods of topological recursion recursively. So, but the computation complexity of these computations, these amplitudes, are order of g factorial and exponential to n. And it's extremely challenging to find asymptotic closed form expressions. Like, for example, in Agrawal, with a very beautiful, very complex, basically analysis, he could, into 2020, actually, after all these 30 years of research, could show basically up until the limit of n being of order of square root of g, the large genus asymptotics to the psi class intersection numbers. And even for large n limit, it still is an open problem. Or if you could basically lose this condition that n is of order of square root of g, still is an open problem. Then another issue with this whole basically aspect of these type of computations is that it's very hard to actually get identities, because these identities are very important to bypass this computation complexity to get basic actual results. For example, for Gromov-Witten invariants, it's a gold mine to basically find such identities to be able to basically provide results for example, genus 80, genus 100, and so on. So it's actually even finding a new identities is very important. So then the simple idea, as I provided in the motivation slide, is that let's circuit this computation, and given the quantum area structure and initial data like A, B, C, D, and the genus and number of mark points, is it possible to basically surrogate this computation, that one can basically create this alignment with this AI mathematician collaboration paradigm? But if this was simple, so let's see how hard it is to actually do this. Is it actually simple to do this? The first challenge is that the data that we are looking at, the data of psi class intersections, they carry a huge amount of heteroscedasticity, meaning that they given that you want to find for a given genus or number of mark points, the values ranges in a huge with a huge variance. For example, if you want to compute it certain, like for example, genus 3, genus 4, genus 5, and so on, the variance that you are basically targeting to be able to like compute such intersections in the log space, sorry, in the actual space, they are of power of 10 to the 30, or 10 to the 20, 10 to the 40. So in a sense, for a basically even one genus or one number of a certain number of mark points, you have to be able to compute within the range of 10 to the minus 45 to the 10 to the power of 45 values. So if and this is only within this window of computation. If you go beyond this, the values grows even higher. So this is one challenge, which is like absolutely not being even approached in machine learning community even closely. So because in machine learning community, you're looking at mostly compact values, even in the regression, like in a forecasting basically, or in a generation task and a forecasting task. All the values are within at most a periodic type basically function. Another challenge for intersection numbers in general, but in this case psi class intersections, is that we are looking at function that is that shows a multi-dimensional recursion. So we are basically looking at a recursion at g and n at the same time, plus the order of recursion is not fixed. For example, let's say that I want to compute a surrogate, I don't know, let's say Fibonacci sequence. It carries a fixed number, it is based on a fixed number of preceding terms, and then you find basically, you can basically compute Fibonacci sequences, and you can also even surrogate this computation with a neural network that has been done, that had been experimented a couple of years ago. However, the recurrence that we are basically talking here, it's not a fixed order. You have to, if you want to compute basically for a certain g and n, an intersection, you have to actually like in parallel solve some sort of a combinatorial optimization to find all the g's and n's that are basically being related to this specific g and n. That's why, like, even like if you want to basically create a very fast code of the whole topological recursion computation, it's extremely non-trivial. Let alone like a neural network want to basically understand such a dynamic, basically a non-fixed order recursive function. So now let's take a look at what the actual values of the function look like. So this is the within the different number of mark points. This is how the psi-class intersections actually blow up. As I said, they blow up factorially. So the red one is the factorial function. The blue line is the double factorial function. So it's basically has values between these functions, as one expects. And if you basically open up these within all the values, like I called it steps, like a forecasting, then this is how high frequency, high frequent basically the values are within the basically the whole steps of the psi-class values. So at the same time, you're looking at basically a function that has a behavior of a factorial function. So then the question would be, how does actually ML performs against such recursive functions? I mean, do we have any do we have any benchmark or some sort of expectation for such neural networks to actually perform? The bad news is that, well, there hasn't been, prior to us, there hasn't been actually any serious work on recursive functions. Then let's create a small two example to see how exactly neural networks perform against a very simple first order recursive function. And let's see if it is, if the model, like any neural network, simple neural network, is able to, after being trained over this part, which is basically a recursive function which follows this equation, is it possible to basically ask the model to not only fit this data part, but also to extrapolate within this test part? Let's see if a two-layer neural network with 10,000 epochs is able to do so. If you use, for example, a two-layer neural network with a ReLU activation function, this is the behavior that you get from the prediction of the neural network, so the orange line. If you ask a tanh function, like a two-layer neural network again with two tanh nonlinear activation functions, this is the behavior of the tanh activation function. If you continue to do so with, for example, sinusoidal activation function, what is called snake activation function, this is a little bit better. So it's giving us hints that, okay, calling sinusoidal functions could be something. And Kolmogorov-Arnold neural network also fails badly over this kind of. I mean, it captures something here, but then it cannot really continue to do so over the whole range of the domain of the function. Then this is giving us evidence. This is giving us some hints that the activation function is actually important in capturing different basically functional behaviors, especially within this recursive function domain. And this is important because you see, almost all problems, I can safely say that almost all problems in enumerative geometry, they also follow some sort of the same recursive behavior. So if you look at this from this perspective, then you can see that actually this is a big problem for neural networks to capture such functions. Then we see that, okay, cardinal linear activation functions fail miserably, even with this very fixed recursive pattern. That's where we introduced dynamic range activator activation function, nonlinear activation function, which is basically provides a learnable sinusoidal plus hyperbolic tangent function that basically carries both a harmonic part and a hyperbolic part. That's basically we want the model actually to saturate along the large values of large input values, and then this is the result. Unfortunately, we couldn't up until now we couldn't show from functional analysis why actually this is working, but from the empirical perspective, the learnable activation function with learnable values A, B, C, D, and with this combination of sinusoidal harmonic part and hyperbolic part, it is giving us the best performance. So in comparison, without adding any like more parameters within the same window of training and testing values, this is the performance that we get, which is much better than the other activation functions. So there is an empirical, I would say, quote unquote, empirical hope that one can capture recursive behavior of psi-class intersections with this new activation function. Now, actually, I'll show that if you basically lose this activation function and you have the same basically procedure, it doesn't happen with the psi-class intersections. But before getting to the results, let's be one with the data and see what actually the problem is from the perspective of like pure machine learning data perspective. So as an input, you have the genus, which is an integer, the first column, number of mark points, which is another integer, partitions, which is our first modality, which is a sequence. I mean, not sequence, but a set, which is a permutation invariant. Remember those symmetric D1 to Dn? These are these partitions. And the tensor B within the initial data of quantum area structure. We chose B. There is a reason why for that. I'll explain later. But if you basically take this tensor and create a coordinate format of this tensor, then this graph, then you will end up with basically a four-dimensional sequence, which carries basically a positional information, because each point of these sequence shows that in the sparse tensor of B, what is the value of this basically quantum area structure initial data, which we basically from now on call B graph in a CUO format. So these are our basically input data for whatever model that we have. In the next slide, you'll see. And we call this input data that has two modalities. The first modality is D, partitions, which is a set, and another modality is a graph in a CUO format, which is B. What is the model? The model is basically a multimodal transformer. So we have the B information in a sequence format, and D information is another basically in a set format, and G and N as a global basically information. They go through two basically transformer layers. Everything here are basically being the activation functions. All here are basically draw activation function, and there's a gymnastics here. If you're curious, you can ask me later. But now I go to the next slide. I want to go through the analysis that we did after, but I don't want to bore you with this technicalities over the model itself. But if you have questions on this part, there are some basically gymnastics that we did to make the model actually work, to capture this whole range of 10 to the minus 45 to the 10 to the power 45 values and so on. But I don't want to bore you. I will go through the next slides to tell you the story of what we could get out of this basically neural network. So, but before that, let's take a look at a bird's eye view of what's happening. So we want to compute basically the amplitudes, intersections, whatever it is. Like here, it's a psi-class intersections. There is an analytical recursive format of doing so to get basically the values. But what we want to do is that we want to surrogate this computation from another basically path to bypass this analytical part to get the values in a reliable way, which is very important. Oftentimes, I mean, not oftentimes, most of the times, unfortunately, in AI for mathematics, people really do not consider this reliability as a huge factor, but actually it is a huge factor because we are actually talking about something exact, not a basically something with error bars or something. And that's why this is the reliability is very important. So that's why we basically create two basically test sets or validation sets. One in distribution setting, which means that we test at the same G as the training, but at higher number of mark points. Then out of distribution setting, which the model hasn't seen before, which is higher genus than the training all by itself. And then we quantify the uncertainty with the conformal procedure, which is very important. Again, I cannot emphasize on this enough because this is very important. Like if you want to predict something and you just say that, yeah, my performance is 90% and I'm happy. And no, in mathematics, you have to be precise up to certain uncertainties. I mean, if you say that my performance is 90% and you go to a mathematician and say that, it's just like, what does it mean? I mean, 90% of what? But if you say that, okay, this is the error bar, this is the basically uncertainty that my let's say large genus asymptotic closed form formula is giving you, and this is my, for example, neural network. If the uncertainty matches, then this is a reliable computation. This is the same with classification. This is the same with regression, and so on. And this is the performance. This is the performance. So on the left side, you see the in distribution setting. That's the model is basically trained with the same genus 1 to genus 13, but the model is basically predicting values within the higher number of mark points. So mark points higher than the model is seen in the training, and this is the result. Which the R2 basically is basically the higher is better. It's basically telling you how accurate your prediction is, but it's not enough. You have to look at the basically the uncertainty quantification, which is being evaluated by its coverage and conformal width. And the conformal width is all of these conformal widths are within the range of the uncertainty that one wants to compute the intersection numbers, given that your error bar is 1 over G. And the coverage is basically saying that how well you are basically how well you are predicting the conformal widths, or what is the reliability of your conformal width. If it is too confident, it's not good. If it is not confident enough, then it's not good enough. So every time it should be around 90%. But it is very important that I should basically say this, that I'm not conveying this message that the model is basically doing extrapolation in a complete sense. So this is important. This is the out of distribution setting prediction, which means that the model is predicting higher genus than training. And then, as you can see, that genus is 14, 15, 16, and 17. The model's performance is decreasing. So this is very important. Here, the message is that even though we are in a good coverage, we are in a good conformal width, the performance of the model is good up until this genus 17. As we are going far from the training basically region, even within this 4 or 5 a number of genus more, the performance of the model is decreasing, which follows basically this classic problem with neural networks, that they are not able to extrapolate beyond by a huge amount beyond the training data. So this is an important message, that even if basically someone comes to you and say that, yeah, I have a neural network that predicts, I don't know, this for me up until genus 1000 without certain basically certain constraints, like, I don't know, some physics informed neural network or something, or another gymnastics. This is most of the case. It's just you cannot rely on that, and this is very important. And here the story is the same. As we are going far from the basically training data conditions, we are basically seeing that the model is basically experiencing some sort of catastrophic forgetfulness. And so up until now, we saw that, okay, the model is performing. This is good. And then the important thing is that how we can extract the knowledge that the model has actually learned up until now. So this is basically what we want to explore further after this. But before that, just let's see what was the performance of actually this nonlinear activation function, the function that we introduced, this draw nonlinear activation function. And as you can see, that if you drop the draw activation function, for example, if you use a sinusoidal activation function or glue activation function, which is a normal activation function with transformers, or ReLU, you can see that the performance is not even comparable with the draw activation function, and it's basically, again, miserably failing. So again, I should emphasize that this draw activation function, the mere participation of this activation function within all the layers of this multimodal transformer of us, it's very important. But then the question remains that do transformers actually understanding the underlying enumerative geometry, like the whole constraints, the whole basically nuances in data, or as I said before, is it possible to extract useful knowledge within this AI mathematician basically collaboration that hints toward a possible discovery of a theorem? There are basically ways that we are exploring this, and in the end, there's an important message. The interpretability approaches that we use are self-similarity approach, causal tracing, or causal inference in the literature people call it, and what we introduce as abductive hypothesis testing or abductive reasoning. I'll go through that in a couple of slides. So let's first take a look at the self-similarity interpretability analysis. So if we look at basically in the internal representation of the last layer before the prediction head of the neural network, so there is there are this intersection numbers. They're being mapped into a vector space of internal representation of the neural network. And now what we do that we extract these internal representations, and then we compute a cosine similarity between these basically vectors of that being assigned to each intersection number, and we look at the cosine similarity. And this is the basically this is the heat map that we get, and this is the filtered version of this heat map, which means that we basically extract a top 99% of highest probability of this cosine similarity. We see this map. What do you think this pattern is? Dilaton equations. Interestingly, the model is actually learning dilaton equations purely from data, nothing else, no constraints, nothing. The model is learning basically sub-equations of Virasoro constraints. So the intersections involving tau1, which is the first exponent of the psi classes, the model is actually picking that. So if we basically plot the dilaton equations, this gives us this, and this is what actually the model is learning. So the model is learning at least the dilaton equations. then what are the other basically the other parts of the pattern? This is actually very important to ask, and this is what actually we are currently exploring. And if you look at the big picture, if you want to find a new identity, you have to test within a huge combinatorial space of order of 10 to the power of 7 number of basically intersection numbers. But now with these patterns, one can basically extract the highest probability of the highest probability samples from this small, basically, for example, patch of cosine similarity heat map, which is basically give you order of 10 to the power of 3 number of samples within this huge combinatorial space. And then you can run, for example, a reinforcement learning model or a symbolic regression model over this much lower number of basically sample space. Then you can find new identities, which is exactly what we are doing at the moment. And this is basically something that we are exploring. This is the first thing that we could learn from this looking at the self-similarity of the neural network. That without the neural network, you should have basically used basically brute force calculation to be able to extract within a much larger combinatorial space. Another way of basically interpreting the results is that let's look at the basically model's decision-making process. How exactly it's associating inputs to the outputs. Or another way, basically, is it possible to identify which input modality is more influential in predicting the intersection numbers? Again, in other words, we want to basically uncover how the network is causally comprehends the underlying mathematics. Let's basically design an experiment. Let's basically say that we have the input modalities B, D, and number. Like B is basically this quantum area structure initial data. D is the partitions, this permutation invariant set, and N is the number of mark points for each instance I. Then we create an experiment. Our basically in 2 steps. Our first step would be a clean run. What we do is that we record all the model's prediction on a regular input. Nothing fancy. We just basically run the model and ask it to predict the values, and we record the autocorrelation of the predicted intersection numbers. The second run, which would be our basically intervention in the causal inference, we form a counterfactual intervention. What we do is that we modify instances in one modality while basically keeping the other modality intact, to observe how exactly these changes, using the counterfactual basically samples for each modality, affects the model's prediction. But we do this per modality, which is very important to see how exactly each of these modalities is affecting the model's outcome. For example, if we have basically this partition, which is originally for n equal to 6, we assigned a sample of n equal to 3 to this partition, and we see how exactly the model is behaving. So this type of basically replacement, or this counterfactual analysis, basically results in understanding the misassignment of the features to each sample and how powerful it is in the final results. So if we do so, we get this result. So on the leftmost plot, you see the actual autocorrelation of the predicted intersection numbers without any in the clear run without any intervention. And on the third plot, you see that we are doing the intervention over the n only, n being the number of mark points, and we are basically misassigning a wrong sample to this basically to this modality, to this feature. What we see is that the model is being affected, and the autocorrelation is being basically affected. We cannot say minimally, but it is being affected up to a certain point. Then we do this for B. And interestingly, we see that if we do this for B, if we assign a wrong sample for the modality B, we see that the model's performance doesn't change. This is important. Remember that here in predicting the intersection itself, the B modality has the minimal effect in doing this prediction. While if we do this for D, the partitions, drastically the result would change. You would lose all the correlation out of the correlation of the intersection numbers. So what we can learn from this experiment is that the model is predicting the intersections mainly relying on partitions and number of mark points. And remember, the B is minimally doing any effect in only doing the prediction, but do not rush into results. We'll see in a couple of slides later that how exactly B is being affecting actually what we want to learn from the abductive hypothesis testing. So the B is present, but not here in predicting only the intersections. So let's see again what we want to do from a bird's eye perspective. We wanted to surrogate the computation, the analytical computation of the psi classes. But then in the end, what is the final basically goal? The final goal is to be able to find a closed form formula for these basically recursive functions for this generating series for these amplitudes or intersections. So we have a network, we have another brain that is predicting values of intersection numbers, and we know that the model is learning some underlying constraints and geometry from the data. So I can say that we are safe to say that mathematicians with less amount of data, but absolutely with more intuitional hints in a inductive/deductive manner, they conjecture closed form expressions for the intersection numbers. But the question is, in scenarios, imagine that the form or the parameters of the symptotic closed form formula for such intersection numbers is absent entirely. And is it possible to rely on an AI-based, basically abductive reasoning model to infer for you, basically, or provide evidence for you for the parameters of the asymptotic closed form formula? So in a sense, what you want to do, like I would just say in the next slide, what you want to do is that is it possible to provide basically to do basically inference to the best explanation in the abductive hypothesis testing. Let's go through this step by step. Imagine that you have a conjectural form of the large genus, for example, asymptotic of psi class intersection. I'm going through this experiment because we already know the large genus asymptotic of psi class intersections. Let's say that this is our conjectural form, which is safe to say that we have basically the psi classes times some coefficients from the partitions, and it's basically of some order of a main body of this form, and some higher order terms. And this higher order terms is not fully known at the moment. I mean, people are still basically going through basically finding more accurate version of these higher order terms. But we have, but they are being called by the polynomiality phenomenon in the psi class intersection numbers, and this whole basically Kontsevich-Wheaton Kontsevich-Wheaton basically amplitudes. So then this is the experiment that we want to do. On the left-hand side, it's being modeled by the neural network. The neural network is predicting this left-hand side. But the right-hand side is a conjectural form. We know that, okay, there is an exponential growth constant that is basically is a parameter of this whole conjectural form of asymptotic formula, given that you change the for example, let's say psi classes to any other basically classes, a couple classes, this exponential growth constant actually changes. Plus the higher order terms, the polynomial basically polynomiality basically part, it is also being changed based on the model, the corresponding intersection that you want to compute. Then what the abductive hypothesis testing does is that it creates a probe in a basically discrete search space. What we want to do is that we want to see what values of, for example, let's say this parameter of the conjectural closed form formula creates the most correlation to the prediction of the neural network. So in a linear probe, we probe all the values that we want to assign or we want to test against each other for example, the value of this exponential growth constant or the values of the higher order terms in a discrete setup. And we want to see what is the highest probable basically value to the understanding of the neural network. So we have to here to basically rely on the understanding of the neural network for the corresponding intersection numbers. But then you might say that, okay, why we don't basically put the values inside of this formula and just be done with it? But this is the trick. You don't have the complete formula. You have the conjectural form of the formula. So you cannot basically say that, okay, the value is basically a rational number and I'm done with it. No. If you want to see what this rational number is in an accurate manner, you have to basically rely on understanding of the neural network. And this is this experiment. That if given that A is a rational number, this is an important assumption, which is a valid assumption for psi-class intersection numbers. Let's grid probe linear or nonlinear manner over the values of, for example, this A, and such that the internal representation of the model predicts the best, basically, gives you the highest confidence over prediction of this value. So what we are doing is that we are basically creating a linear probe over this 10 by 10 grid for this A, and we ask that, okay, now that you have the understanding of the left-hand side, give me what is the most accurate A that predicts the left-hand side for me. And if we use a linear probe, it gives us with a good confidence that the value 2/3 is actually the value. And if you use a nonlinear probe, then with a higher confidence, we see that 2/3 is being embedded in the internal representation of the neural network. So what we are saying here is that this A, the value A, which is an exponential growth constant, which is related to the underlying quantum curve of the basic Airy quantum curve of the psi-class intersection numbers, it is being encoded into the internal representation of the neural network, and it is being associated to a certain basically entity that I will go in the 2 slides from now, but it is associated to something in the data set. So this is so we are basically safe to say that this A is being non-linearly embedded in the internal representation of the neural network. And also the same thing for the polynomiality phenomena. So this higher order terms, if we do this for the higher order terms of A, alpha 1, alpha 2, and so on, like on the first 2 alpha, we'll see that again, the same thing persists. So the polynomiality phenomenon is also being internalized by the neural network in a non-linear manner. And then this is the one thing that I wanted to reach. Remember that we did this intervention, this counterfactual analysis over basically N, D, and B, and we were basically saying that if we do the intervention with, for example, changing the N or changing the D, had the highest basically drastic change over the autocorrelation of the predicted values. So if we basically quantify this autocorrelation by this R-squared metric, then basically you can see that if we don't do any intervention, the R-squared is 96%, which is very high, which is the actual prediction of the neural network. If we do this with the N, it drastically drops. Remember, the autocorrelation just basically got a little bit lower, so you lost the correlation between the intersection numbers. If you do this with D, the partitions, you were losing the entire autocorrelation, which is now giving you R-squared of -52, which is very bad. But now And you remember B had a minimal amount of effect on this basically intervention analysis. So we were basically inferring that B has a minimal effect in prediction of the intersection numbers. But now if we do so over predicting the coefficients of the closed form formula for the psi class intersection numbers, large genus closed form formula of psi class intersection numbers, then you see that actually B has the highest performance or highest effect in changing the basically performance of the model. So if we do the same intervention, but now only what we look at is not the autocorrelation of the psi class intersections, but actually we look at the performance of the probe that we introduced this abductive hypothesis testing. We'll see that B has the most effect. So in a sense that the model is implicitly learning the asymptotic closed form formula expression of the intersection numbers, but with only limited amount of data. So here what the message is that in order to infer or extract knowledge for the large genus and number of mark points of the different intersection numbers, you don't need to have access to a huge amount of data. It is possible to infer at this point, basically in our work until now, we are exploring further now to get the complete closed form formula. But up until now, we are safe to say that we are able to extract the coefficients of the closed form formula only given this limited amount of data. And we now can basically trace where exactly these information actually being carried out through the network, and that is through the quantum area structure initial data. So they are not basically creating a minimal effect over the prediction of the intersection numbers. They are actually basically being internalized by the neural network to give the neural network the understanding of the asymptotic closed form formula for the intersection numbers. So if I want to basically finish the slides, I want to go through basically a short history. So in 1991, Wheaton proposed a recursive formula for generating all the intersection numbers of psi class psi classes through this KDB hierarchy. In 92, Kontsevich proved Wheaton's conjecture through matrix models and combinatorial methods. In 2004, something that I skipped because this was not directly related, but is related to the whole picture. In 2004, Mirzakhani basically offers a novel proof to Wheaton's conjecture to basically not for basically algebraic curves, but for the volume of moduli spaces of hyperbolic surfaces with hyperbolic structure. And she basically provided a closed form formula for this computation. In 2007, Enaud and Orantin provided the actual formalism topological recursion, which is basically the underlying recursion behind almost all of these basically almost all of the enumerative geometric intersection numbers, safely to say, almost. And in 2018, Kontsevich and Zeugelmann provided a linear algebraic perspective of this whole topological recursion, which basically paved the way for introducing the neural network perspective to this. And they basically provided this quantum area structure formalism. And in 2024, we basically tried to provide a neural enumerative reasoning model to be able to basically capture this highly recursive psi class intersection numbers, plus being able to extract knowledge from the understanding of neural network and show that actually we are able to, with a systematic procedure, we are able to infer not in a deductive manner, but in an abductive manner. We can infer basically parameters of the closed form formula of the intersection numbers, and we show that the closed form formula is actually internalized by the neural network, and it is possible to extract the whole formula, which is the next step of this project. Thank you very much. Any questions?
you hear me? Oh, I can hear the echo. Hello?
I can hear you, but
Oh, good. Yeah, I was gonna ask, let me see if yeah. We haven't set it up well here, but to make the very short question, if you've looked at symbolic regression, that type of technique for actually finding formulas might be more interesting for getting exact results.
yes, exactly. This is the next step that we are exploring at the moment. Yeah, that's because this was not clear. Like, if so, you see that if you want to find an exact formula for a large genus asymptotic of certain data, then you have to have a priori. You expect that you have to have basically all the data up until large genus, what you define to be a large genus. But what we now are showing that it is not necessarily needed to have that, and the model is basically with much less amount of data, model is basically internalizing this closed form formula for the large, aka large genus or large number of mark points, basically formulas, and we are able to, the next step, provide a symbolic basically format of this formula. Yeah.
I have a question. The first half of the talk, where you compare the different activation functions, you go to that slide. So it looks to me that you have a lot of problems because of the oscillation. The two, and maybe also because of the growth at infinity. Yeah. Exactly. So two things. Have you tried to sort of estimate, like, don't try to fit R, but fit R minus N, where the thing probably is bounded, still oscillating, and then to deal with the oscillations, maybe to do some kind of Fourier transform or something like that. Is there a way?
We're transforming the Rn function, you mean?
The two things, yeah. So first, subtract the N, and a new recurrence for R minus N.
Just this part, you mean?
Yeah, exactly. But then it should be rewritten in terms of like this R of N minus 1 needs to be rewritten in terms of like the new function, which is R of N minus N. So that's one thing that perhaps it could improve the performance because you don't grow at infinity anymore. And then the second thing that I don't know if you've tried it or not, but maybe to deal with the oscillations, taking some kind of Fourier transform or something along those lines could potentially help.
Yeah. So the first part I haven't explored subtracting n and seeing if basically that helps. So my main motivation for basically considering this was that I created a toy example for basically a controlled environment incubator so that I can check what basically the contemporary and normal nonlinear activation functions actually perform against this very simple problem. But then on your second question, I actually did not consider a Fourier transform of this, but I considered basically random Fourier features, which is basically, this was introduced in 2021 for high frequency data. They basically provided some sort of embedding of high frequency data and then applying a neural network on top of that. I actually checked, and it was performing much better than these basically nonlinear activation functions. But the Fourier features are not nonlinear activation functions. They are basically sort of an embedding layer. So if I basically do nonlinear activation, if I do basically Fourier features and then all these activation functions, they perform better, but still they're not basically extrapolating through the test set. So you see here I want the model to be able not only to capture this part, but also to be able to basically extrapolate to this part. So in a sense, I'm asking the model to this 2-layer neural network to be able to learn the actual function itself up until this point. So that was my motivation in a sense. Yeah.
Yeah, thank you.
Okay, let's thank the speaker, and yeah, so that's it for today. And thank you so much for giving the talk.
Thank you very much. Yeah, thanks for inviting me.
Thank you.
Bye.
Thank you. Bye.